world-class NASA STEM Stars team. From NASA centers across the country, we present Chris Good.
Hey, STEM fans, welcome to this week's episode of STEM Stars. It's a chance where we get a moment or time to reflect and see what's going on at NASA and chat with STEM professionals from all across the agency. I'm so excited to welcome our guest today. Before we get started, my name's Jen Hudgens, and I'm coming to you from the Kennedy Space Center in Florida. It's a little bit rainy today, but we're going to keep that rain away. We're going to talk about something exciting. The James Webb Space Telescope. So our guest today is Chris Gunn. He is a photographer with the program and with NASA. So I'm really excited to find out what you actually do as a photographer when you work for NASA. And I want to share with you what our agenda is going to be for today. So we're going to chat with Chris. We're going to meet him, find out what his background is, his education, find out how he got started as a photographer at NASA. You'll have a chance to ask all the questions that you have in the chat box, and we're going to learn more about what your mission will be at the end of today's episode and then what's going to be on next at NASA STEM Stars. So if you have any questions along the way in today's chat, drop them in the box, and we'll get those to Chris as soon as possible. So welcome, Chris. How are you doing today?
I'm doing great. Glad to be here.
So you work out at the Goddard Space Flight Center in Maryland. So hopefully your weather is a little bit better than ours today.
It's really
do you mind
nice.
sharing? Oh, good. I'm glad to hear that. I wish it was nice here. Well, it's thundering and lightning and storming outside. So tell us a little bit about yourself and what are you interested in outside of your job at NASA as a photographer?
Well, I'm Chris Gunn. I do work at NASA's Goddard Space Flight Center as a photographer. I really enjoy cycling on my off time and working on cars. My interests outside of work tend to revolve around science and science communication, just learning more and more about science of all types, especially space exploration and photographic art.
Can you talk a little bit about science communications? What does that entail?
Science communications, I guess, is what really got me involved in science to begin with. When I was a kid, I loved reading. And I loved reading books that made science digestible for me, that I could understand. And I think science communications revolves around having scientists and engineers, anybody in any science field, boil it down so that the average person can understand the science. Right, so to interest everyone from young and old. So that's nice.
So,
and I'm involved. Go ahead.
Yeah, I was going to say, so it's kind of storytelling in whatever medium that you decide.
Exactly. So I'm involved in science communications because I create wonderful illustrations of the James Webb Space Telescope. That's the current project that I'm working on.
So, I was going to say, is there a degree for science communications, or tell me about your path through school?
So I have a very interesting path through school. I started off in college wanting to be a lawyer. So I went to Morehouse College and I studied political science. After school, I actually started working at a law firm as a clerk and a librarian. And I found it not very interesting, to be honest. It was a wonderful organization, a wonderful law firm, and I happened to meet one of the lawyers there who was a film professor at a local university here in Washington, D.C., and I told him of my interest in photography, and I actually had a portfolio, and he took a look at it, and he said, "What are you doing here? Why don't you pursue your passion?" So I actually went back to school at the University of District of Columbia here in Washington, and I studied photography. So my degree is in photography, and I opened a studio right after that and started producing photographs for magazines and newspapers and universities and that sort of thing. And about 10 years into that career, I found out they were offering a job at NASA Goddard Space Flight Center. And I applied for it, and I took it.
So the job was actually in photography for NASA.
The job was in photography for NASA, and they were looking for someone that could produce portraits, group photographs, of day-to-day life at NASA. And I worked there, and then someone asked me to join the last Hubble servicing mission, where I actually photographed the work that was behind SM-4, which was the last Hubble servicing mission, the mission to service the Hubble Space Telescope.
So are you telling me that you can work at NASA and be an engineer or an astrophysicist?
Well, yes. I mean, you can be a writer. You can be a photographer. You can support the missions in all types of ways. And communications is very important at NASA. I mean, everything that we do is communicated to the world. And part of that communication is writing, imagery, that's illustrations, that's photographs. In fact, if you think about one of NASA's most famous missions, the Apollo mission to the moon, we wouldn't know anything about it if there weren't photographs, right? So photography is part of NASA's mission. That's how I view it.
So we had a student ask a question, actually. Do you have a favorite photograph or testing milestone that you enjoyed photographing the most?
Well, I've been working on the James Webb Space Telescope for the last 10 years, and I could probably count to 4 or 5 images that are some of my favorites to date. And I'm actually going to show you some of those later. Well, in fact, here are some of them. Here are some of my favorites, actually. So The first image, if we're reading from left to right, is actually what the telescope will look like when it sits on top of a rocket. Okay, so that is the final configuration of the telescope, and this photo was made just before it was taken into testing most recently. So if you were to say a favorite photograph, that's definitely one of my favorite shots right now. The next image, the middle image, is a photograph of some work being done on the telescope, on the optical portion of the telescope. So what you're seeing there is not the entire observatory, but the optical portion of the telescope, which includes the 4 instruments that make up the telescope. And that last photograph on the end is actually a testing milestone, and that was when the telescope's secondary mirror was deployed. This telescope has a secondary mirror and a primary mirror. The secondary mirror was deployed, and that's the first time and only time that mirror will be deployed here on Earth. So these are 3 of my favorite photographs right now.
You definitely make that telescope look gorgeous. I can see that the reflective surfaces of those lenses are so beautiful.
Well, the telescope is beautiful, and part of my job is to create images that are both technically accurate, and when these images get pushed out to the public, for the public to see, I do want them to be striking, and I want people to look at them and then learn more about the telescope.
So before we get ahead of ourselves, Chris, I know you brought a video with you today that kind of tells a little bit about the James Webb Space Telescope, and it's a time-lapse video. So when students watch it, they'll see the satellite open and close, I believe, in the video. So we take a look at that video, and then we'll explore some more of your photographs of the project.
Let's take a look at the video. Sounds great.
Thanks. Wow. So that telescope looks ginormous. So can you relate in size for the students about how big the telescope is in comparison to Hubble, maybe?
Well, the telescope itself is made of 2 components. And what you saw there in the beginning of the video, of the time lapse, was the optical portion, the mirrors and the instruments, actually coming over right, and being joined with the sun shield and the spacecraft itself, the spacecraft bus. Then you saw the sun shield actually deployed, so open up. And that sun shield is about the size of a tennis court, okay? The mirror itself is 6.5 meters, which makes this telescope about 100 times more powerful than the Hubble telescope itself.
Okay, so just a couple more questions, if you don't mind, from our students. They're flying in here. So, a personal question: are you a media personnel for NASA? I guess they're asking if you work for the Public Affairs Office, or are you directly connected with the Webb telescope?
So, both. My job is two-pronged. I'm both a technical photographer as well as an office of communications photographer. So some of my photography is used purely for engineering purposes, and other photography goes out to the public through the Office of Communications.
Perfect. So there's another question about photography. Is there a specific way of photographing the satellites, or is it just normal photography? Do you use special cameras that we don't normally see? Or I guess that's the question they're asking.
I use normal cameras, but one of the things that I aim for in my photography is to have distortion. To see is basically what the telescope looks like. So I try to avoid really hard angles or skew sort of thing. So I look straight at the telescope, and I want to create the most perfect pictures I can. Like this one behind me. If you can see it.
Oh, yeah. Is there a particular camera you like using? A student has asked that. So what camera do you use? I'm sure you have several, but you might have a favorite.
So I use 35 millimeter digital cameras. I also use medium format digital cameras, which makes it so that I can blow the pictures up really big.
Okay, so some of the other questions have to do with the Webb telescope in general. So why don't we take a look at some of the other photographs that you brought with you today, and maybe we might get to answer some of those questions during our discussion. So what are we looking at here?
So here you're looking at tests and also locations as to where the telescope itself was tested. So that first test is showing you how they might clean some of the mirrors at some point. This technique has actually never been used to clean the mirrors, but it's a really interesting shot. They're blowing carbon dioxide snow onto a mirror, very similar to the mirrors on the telescope, and they're cleaning the surface with that. They've never used that technique on the telescope itself. The other photograph, the center photograph, is one of the locations that the telescope is tested in, and I just thought it was an amazing location. I get to photograph in really incredible spaces. This particular space is used to test the telescope, the communications of the telescope, see how the telescope will do in space. They shoot radio waves at it, if you will, to see how the communications will be. And then that last photograph with the pink wall, that is the room where the telescope was actually, the mirrors were assembled. So that is the clean room, and that wall there are all the filters in the clean room, right? So that's how they keep the clean room so clean. Next slide. Okay. These are two great photographs. That first one there on the left is the videographers on the team, as well as myself, had an evening with the telescope, if you will, after some testing, after some successful testing, and we were able to turn the lights down and create really, really nice lighting so that you can see how beautiful that mirror is. And that image on the right is a shot of the telescope at NASA Johnson Space Center. That's inside of a test chamber. The primary mirror is deployed, the secondary mirror is deployed, and it was a 90-day test where they actually took this telescope down to the temperatures that it will see in space to make sure that everything was going to work. And I made this photograph right after the test was completed.
Students want to know, is there going to be a webcam on the telescope where they can see it working in space?
Unfortunately not. I would love for there to be one. In fact, I would love to go and photograph myself, but no, there won't be a webcam on.
Well, I know, like for the Perseverance rover, there was a webcam that you could tune in and see what the engineers were doing. I don't know the answer to this question myself. Is there something like that where we can peek in and see the work that's occurring with the telescope here on Earth?
So there was for years when the telescope was here at the NASA Goddard Space Flight Center. Now the telescope is in California at Northrop Grumman for the final testing and there are no cameras in that facility. And that's one of the reasons that I go out periodically to make photographs so that you can see the progress.
Oh, gotcha. So you are truly our storyteller. Thank you. Thanks for sharing the story.
My pleasure.
What's the purpose of the Webb telescope? Is it going to take the place of Hubble, or what is its job going to be?
Well, as you know, the Hubble telescope is science. The James Webb Space Telescope is the successor to Hubble, but it works in a completely different range in terms of light. So it works in the infrared range. And what that's going to do is allow us to see further into space and back in time, if you will. So we'll be able to see some of the first light from some of the first galaxies that Hubble was not able to see.
Amazing. That's so amazing. I can't wait to get that into space. Are you going to be at the launch, or where are you going to be during the launch of the Webb telescope?
I plan on being in French Guiana for the launch. It's launching from French Guiana in South America on Halloween 2021.
All right. That'll be a good trip, and I'm sure you'll be very proud to see that finally lift off. All right, I know you brought some more photos because that's what you do. So let's look at some more of your pictures that you brought of the telescope. What are we looking at here?
On the left there, that is the solar array, which is going to, that's 4 of the 5 panels of the solar array that's going to provide power for the telescope during the mission. That really interesting picture in the center there is the telescope when it was here at Goddard Space Flight Center during a nighttime contamination control peak at the telescope. They turn all the lights off and they look at the telescope, every inch of the telescope with lights, with flashlights. So this particular image is a time exposure. The camera shutter was open for about 2 minutes, and that's why all the people are blurry and the light seems really eerie. The image there, the last image with the 5 guys in the white suits against the white background, they're actually closing the doors to the telescope's transportation container. And that's one of my favorite pictures. It just shows that a lot of people are doing a lot of different things in the project. It's really interesting.
Love it. I think there's another slide of some more images of Webb.
Yeah.
Oh, there we go.
So this is an illustration, I think, of the many faces of Webb, if you will. So I'm actually going to start from right to left describing these. So that image on the right with the 2 gentlemen standing in front of the huge primary mirror was done just before a big optical test that they were going to do. And that is the entire 6.5 meter mirror, primary mirror of the telescope in its full glory. And that gives you an idea of the size of that mirror compared to those 2 guys on the floor there. The image in the shows how the telescope is folded for launch, right? So one of the wings is folded back. So you have, we call those wings, and then there's a center section. So you have the 6.5 meter mirror with one of the wings with the 3 mirrors on the side folded back as they're doing another test there. And that final image there on the left is actually the image of the telescope folded for launch with the sun shields partially folded. So that gives you an idea of the different parts of the telescope, as well as how it relates to the size of those technicians down there at the bottom.
The students are asking, are the mirrors made of actual gold?
The mirrors have a layer of gold on them. So the mirrors themselves are made out of beryllium. They chose beryllium because it's very stable at the temperatures that the telescope is going to see. But the mirrors have a layer of gold. In fact, hopefully I get this fact right, but all the gold on the mirrors, all the gold on all 18 of the mirrors is about the same, weight as a golf ball. So it's not that much gold, but it is actual gold on the top of the mirrors. Yes.
What's the benefits of using gold?
Gold happens to reflect infrared light better than just about anything else. So it's used for its optical properties. Yep.
Very good. The students are asking, and maybe we can show the next slide because it kind of shows what your life is like at NASA. Are you going to be assigned to a new project once Webb launches?
I hope to work as a photographer on the Nancy Grace Roman telescope. That is it's a wide field infrared telescope, and it is slated to begin construction now, actually, at the Goddard Space Flight Center. So that's what I wear when I not the shot of me with the hair flying, but the shot of me with the camera in my hands. I actually wear a clean suit whenever I go into the clean room, just like the technicians. I have to wear the clean suit. I have to wear the mask, the gloves, the booties, everything. And my cameras have to be clean before I actually go into a clean room. Now that shot of me on the right, there is me during the zero-G flight. We were like a really brief project, but that project flew in a zero-G camera, and one of the guys was nice enough to take this picture of me, and it was a lot of fun.
Oh, I bet that was a lot of fun. So that's an airplane that you can take a flight, and it does parabola flights, and you occasionally gain weightlessness, just like an astronaut. So I imagine that felt amazing.
Yes, it was a really amazing feeling.
Yeah, don't forget about putting those questions in the chat box. You guys are doing a great job so far. We've gotten some really good questions for Chris. So let's see, I can ask you some more while we've got a pause here. What orbit will the James Webb Telescope attain?
The James Webb Space Telescope is not going to orbit Earth. It's actually going to orbit the sun, just like we do. It's going out 1 million miles from Earth, and it's going out so far so that the radiation, the heat, the light from Earth will not affect the telescope itself. So that particular orbit is called L2. The green.
Someone's addressing you're wearing the bunny suit there. So why is such great levels of cleanliness needed for making and transportation of the telescope? So why the bunny suit? Are you protecting yourself or are you protecting the telescope?
We're protecting the telescope. We don't want any dust, any hair, any fibers from our clothes to actually interfere with the operation of the telescope when it's in space.
Very good. Why is the telescope so long?
So long. So big?
So I think when it deployed, you see that long bit that comes out in front of the big mirror. So yeah, why is it so long?
So the largest part of the telescope is the sun shield. And it is what it sounds like. It's a shield from the sun. So just like you might have an umbrella to shade you on sunny days, we need to keep the telescope cool and in the shade. So that sun shield blocks the telescope's instruments from the sun, because this telescope needs to operate really, really cold.
Very good. Okay. So will there ever be a possibility to repair the telescope if there is an issue?
Well, I think that we won't have any issues. I think that's the hope. And I'll never say never, because I'm not an engineer and I've always been amazed, but there are no plans to repair this telescope.
Okay. Oh, goodness. Do you know how much money this telescope costs? That's a big question.
I've heard it's a lot.
I've heard a lot too. Let's look at some. You did bring some larger pictures that I want to share with the students before we run out of time. So there's one of someone, it looks like they're being reflected in the mirror. Can you explain this photo to us?
So the mirrors were made in the United States by a company, and that company sent the mirrors to us basically one by one. So this was actually the first mirror to arrive at the Goddard Space Flight Center, and they're inspecting it. They're looking it over inch by inch to see if there are any imperfections, if there's any contamination, because that's what we need to do in order to make sure that this telescope is perfect. So this was the first mirror to arrive.
Perfect. Let's look at the next one that you brought. Is Webb the only project you've worked on for NASA while we're waiting for the next photo?
I worked on Hubble.
Oh, Hubble.
On the last
Okay.
Hubble study.
And the student asked if you had taken a picture of Orion for the Artemis program, so you haven't had a chance to go and do that yet.
No, I haven't. So
Okay,
so
this is my favorite picture.
it's one of my favorites too. This is an engineer. His name's Ed, and Ed is at the bottom of a chamber called the Space Environment Simulator. So the environment that he's in is designed to get really, really cold. But believe it or not, there are certain parts of the telescope which need to be kept really warm. And they use special heaters on those parts. And this blanket was also designed to keep some of those parts a little warmer than their super cold parts. So he's getting that blanket in place. It's called a thermal blanket. And I just had to make this photograph because it just looks really neat.
I've actually seen those thermal blankets used in like emergency preparedness kits. Are those similar to what you're using there at NASA?
It's very similar. Very similar.
Yeah.
Yes.
It's like a tinfoil blanket. Interesting.
Right. It's lightweight.
And then we have
but
one. Yeah.
Go ahead. No.
I think we had one more photo that you wanted to share with us before we get to the students' mission for the day.
Okay. So this is another peek inside of the inner operations. So each one of those mirrors came in its own special container. It's a container sealed environment. So the environment inside of the container is sealed, and so no contamination can get in. And I just thought it was neat how these guys had to push the mirrors around the space flight center there. And I wanted you to see this shot.
So do you think Webb is going to compete for Hubble as far as the legacy of the two telescopes go, or do you think Webb is going to be a completely different story than what you told with Hubble?
I think that Webb will continue the story, and I definitely don't think that it will compete, but it will augment, it will add to the story, and it'll give us more insights into our universe. So I think we need both of them.
I agree. So in the last few minutes of our episode today, Chris, do you have any final advice or tips for our middle and high school students that may be watching?
Well, if you look at my story, I've come full circle. I had an interest in science and engineering. In fact, that's what got me into photography to begin with. And I didn't necessarily pursue my pure interest when I first went to college. I actually recommend that you look at what your interests are, look at what your passions are, and take a long look at the schools and what they might offer you, and follow your heart.
I love it. Follow your heart. That's a good way to end. So we're going to challenge students today to an activity. They've got their own mission. And what they can do is actually create their own bookmark about the life cycle of a star. There's going to be a lot of work that Webb's going to be collecting and a lot of data that we're going to learn thanks to the Webb telescope. So students can begin their journey of knowledge about the life cycle of a star by creating their own bookmark. And you can visit the bookmark and the activity and the supplies that you'll need at the link, and we'll put that in our chat box for you. And be sure to share your work with us on social media. And I just want to take the last few seconds to thank Chris for joining us today. I hope you had as fun as I did. And I want to encourage the students to follow your heart, and we'll see you next time.
Thanks for having me.
Throughout my career at the European Space Agency, many signals, first attempts, landmarks. Looking back, they may appear like isolated events, similar to a collection of single dots on a piece of paper. I want to share the knowledge that I gained along with my journey while connecting these dots. My name is Paolo Ferri. Welcome to my masterclass. Smart One was a technology demonstration mission. The objective of Smart One was to demonstrate in space the utilization of a novel propulsion technology, ion propulsion engine. The technology which is used today for Bepi Colombo at that time was still in its first steps. So we decided to send a spacecraft to the moon, which is not around the corner, but it's relatively far to allow the demonstration of this technique. The end of the mission for Smart One was dictated by the fact that the spacecraft ran out of fuel, and it was very gently, very slowly spiraling down to the surface of the moon. It was getting lower and lower. Our flight dynamics experts had predicted that eventually the altitude was below enough to hit a hill about 1 kilometer high on the surface of the moon at a very precise moment, which happened to be around 7 o'clock on a Sunday morning in September 2006. Just a few days before, in fact on the Friday before that famous Sunday, a scientist, an American scientist I think, provided us with a better orographs that, according to his calculations, the spacecraft would have hit the rim of a crater on the surface of the moon in the orbit before, so 6 hours before the predicted moment of the crash. We had really no alternative information. We didn't know whether he would be right, we would be right. But this was, of course, a very dramatic moment. It was Friday night, and we had invited everybody for the end of mission event on a Sunday morning, VIPs, directors. It was impossible to change the time of this event at that point. I mean, telling them instead of coming in at 7 o'clock in the morning to come at 1 o'clock in the morning. So we had a emergency meeting in our control room, and in fact, Flight Dynamics at this point came up with an idea, and an idea which was absolutely non-orthodox. We had run out of fuel. In principle, we had no way to change the orbit of the spacecraft, but they thought, well, there was still some that was used to offload the reaction wheels. So the ion thruster could not be used anymore to change the orbit of the spacecraft. So they used thrusters which were on a different location on the spacecraft, which were there just for reaction wheel offloading. So of course the spacecraft had to be turned so that the thrusters could push in the right direction to accelerate its velocity and therefore increase the altitude. So this was the idea. This was the proposal. Everybody looked around. It looked in principle feasible, and then the teams went off to implement this very, very unorthodox solution. And then eventually on the Sunday morning, when the previous orbit, the 1 o'clock time passed, we saw that the spacecraft had survived. So it had managed to fly over the rim of this crater, thanks to the very small change in the altitude that we have managed to implement. And then the happy end was that at exactly the predicted time, the spacecraft hit the hill that was predicted originally 7 o'clock in the morning on Sunday, 3rd of September 2006, with everybody present, and success eventually was achieved. So this is an example of how, on one side, thinking out of the box, and on the other side, flexibility of the spacecraft allows solving a problem which apparently is not solvable. One day, one of the 4 cluster spacecraft coming out of an eclipse, cluster went through periodically an eclipse phase, coming out of the shadow of the Earth. At the first contact, did not transmit any telemetry. So we basically, our team was sitting in the control room and not receiving any information from the spacecraft. The station was still receiving a radio frequency carrier. So the signal was there. We knew that the spacecraft was there, and we knew that it was transmitting. But for some reason, our control systems were completely blind. The team did some investigation first, tried to command in the blind the spacecraft. It was clear that when cluster was coming out of the eclipse, and it was sort of switching on gradually all the units, the switch on sequence of the units obviously had not worked properly in this state. So this was clear, but we didn't know what the state was. There was no information. So the team sat there and decided, well, we have only one source of information, which is the radio signal. Is there a way we can do some tests by commanding, try to modify this radio signal, the shape of the radio signal, to see whether commands are received and to see whether we can get out of this situation. So that's exactly what they did. They selected commands that could modify the shape of the radio signal. For example, the height of the radio signal by switching on and off the ranging transponder, you could see that this height would change. And so we sent these commands, and in fact, we noticed that the shape, the height of the radio frequency carrier was changing. This was very important. It showed that the spacecraft was able to receive commands. This was, of course, not enough, but already a very good step forward. Then they went on with this by sending commands that would activate or switch on the onboard computer, and they saw that those were not received. So relatively soon, they could discriminate and they could say, good, the spacecraft is receiving a certain type of commands and executing them, what we would call hardware commands, but it's not decoding software commands. So we knew the problem was not a hardware problem. It must have been something in the onboard computer that was not able to decode the software commands. The team went on with this investigation, and by trying possible sequences of commands, it focused more and more onto the status of some relays inside the onboard computer. Relays that we normally wouldn't change before the eclipse, but that possibly would have been put in a wrong position by this slow ramp up of the voltage at the exit of the eclipse. And in fact, by looking at the design and by trying various potential configurations, at the end, they came to switch the right one, so to set up the proper configuration in the onboard computer, fortunately by hardware commands, so they were received. And about 48 hours after the moment that the problem occurred, by working practically uninterruptedly in the control room, the cluster team managed to reacquire telemetry. This was, of course, a big relief, an incredible success. And once they had understood what the problem was, they could very easily design a procedure that, in case this problem would reoccur, would reset the configuration of all the relays to the right situation. In fact, it happened many more times in the cluster mission because all the spacecraft were periodically going through this eclipse and they were exposed to this potential problem. The story here is, again, thinking out of the box. Look at the tools that you have and try to get the best out of it. We're normally used to our tools is thousands of parameters in the telemetry. At that time, the team had none of them. All it had was the radio signal. But they said, okay, how can we use this tool, the radio signal? How can we get information out of it? They managed, with the incredibly small amount of information, they managed to get out of the dangerous situation. EXOSAT was a satellite built in the 80s, and at that time, the majority of satellites were built still with hardwired logic. So basically, integrated circuits that would have all their functions hardwired. There was no way to reprogram them. But EXOSAT was the first ESA spacecraft which actually carried on board a reprogrammable onboard computer. It was not there to drive the spacecraft. So all the logic of the spacecraft, of the platform, was implemented in hardware. This onboard computer was purely designed to do an onboard processing of the scientific data, to reduce them, compact them, elaborate them so that they could be transmitted in a more efficient way to ground. So only purpose was scientific. We had a dedicated person, a lady in the team, was specialist of this computer, could reprogram it, and she was trained to adapt the programs to the processing of science. One day, the logic of the attitude control subsystem, the failure detection logic of the AOCS, basically failed. And the AOCS was detecting gyroscope failures, even if there were no gyroscope failures. And since this was a hardwired logic, there was no way to change that. So every time there was a spurious detection, the spacecraft would trigger a safe mode, consume fuel, was to interrupt the scientific observation. It was really disaster. It was getting the mission basically to the end. So the team here thought, well, why don't we use the science computer to implement a very small routine, a more intelligent routine that will prevent the spurious triggering of gyroscope failures. So this routine was implemented by this lady very, very rapidly in very basic assembler code at that time, where basically the routine would check itself the gyroscope health, and if the gyroscope was actually healthy, it would keep the hardwired logic of the AOCS disabled. But if it would detect that there was a gyro problem, it would enable the hardware logic, and then the AOCS would trigger the switchover of the gyro in the safe mode. Since we implemented this, no more spurious failures occurred, and the spacecraft continued, the mission continued. So it was a way to save a problem in the hardwired logic of the spacecraft with the only flexible part of the spacecraft that was there, a reprogrammable onboard computer. Nowadays, all spacecraft have reprogrammable computers. We don't have this problem anymore. But that was the start of this new technology utilization.
back to NASA at Home Spaceport Series. I'm Joshua Santora, coming to you from near the Kennedy Space Center. We took a long summer off. Hopefully you caught two huge missions we had, the Demo 2 commercial crew mission, as well as the Mars 2020 launch, part of the countdown to Mars that still is on track to wrap up in February as we park Perseverance and Ingenuity on the Red Planet surface. For the next few episodes, we're going to be honing in on this theme of what does it take to get humans into deep space. Now, this will by no means be exhaustive, but we're going to unpack some of the ways that the spaceport that we so dearly love is playing a role in lots of different ways. Things you probably aren't even thinking about, but are really critical to success as an entire strategy. This is not a small thing to do. Today, we're going to get into the commercial crew program. Like I mentioned, Demo 2 had a phenomenal mission with Bob and Doug on board, getting them home safely, and now gearing up for Crew 1, the first operational mission that SpaceX will be servicing with 4 crew members. More to come on that in the coming days. We're super excited for them to fly and increase the research capacity of the space station. Right now, we're going to get into the question of how does commercial crew operating in low Earth orbit help us get into deep space? And I'm joined now by Kevin Vega. Kevin, thanks for being here.
Oh, you bet. Exciting times.
Kevin, the agency has been about the commercial crew program for about a decade now. When you think back on what's happened and where we are in the history of human spaceflight, how do you process this moment?
Oh, it's historical. I mean, reaching back all the way from when I started this program, which was way before it was even a program. It was kind of writing policy to start this program up. This experiment that is commercial crew was a new way of NASA doing business, using commercial partners and partnering with them to go execute, our crew rotations to the International Space Station and maintain our presence on there, which we had a huge investment in building during the shuttle program. So we haven't had much time to pause, but I think after Doug and Bob landed, for Demo 2, we all kind of took it in and really appreciated the history that was just made for our country.
Your title is Performance Lead Engineer for the Commercial Crew Program. That's kind of a mouthful, but I know there's a lot that goes into that. Can you kind of unpack what your role is for Commercial Crew?
Yeah, my area covers the entire vehicle, so that includes the Dragon spacecraft on the SpaceX side and Falcon 9, and the entire mission duration. So launch, if we had an escape, all the way through rendezvous, proxops, docking, and then of course entry, descent, and landing. All those mission aspects. So the specific disciplines in my area include aerodynamics, aerothermal, guidance, navigation, control, parachute systems, natural environments, the coupled loads analysis, and dynamic environments.
I know you did work operations for the shuttle program back before it ended in 2011, and we're finally into an ops mode here for Commercial Crew. Does this feel familiar, or is this different?
Yes, it brings back old shuttle flow memories when we would have some overlaps with different pieces of hardware over at KSC, and operating a mission at the same time. So this emulates that. This is probably a little bit quicker pace because, we came out of the in-flight abort test earlier this year, and then we hopped into Demo 2, and now we're progressing into Crew 1 fairly quickly after Demo 2 landed.
As you personally kind of think about where we are in the history of human spaceflight, thinking about the past and the future, what's the one thing that you're the most excited about for the Commercial Crew program?
For me, the biggest thing is really our continued presence, having our crew continued presence on International Space Station. But for me personally, it's been really the beginnings of being part of this program from before it was a program, seeing it through certification and now the operational state that we're venturing into.
Kevin, thank you so much for joining us. I appreciate your time and your insight. Good luck to you and your entire team. I know you guys have a lot of work ahead of you, and we're excited to see you succeed.
All right, thank you.
All right, so Kevin gave us a really great insight into what's happening down in the weeds of the program to kind of pull back a little bit and get some broader perspective on the history and future of Commercial Crew and how it's playing into deep space exploration. I'm joined now by Kyle Herring, who's a public affairs officer who usually reports to the Johnson Space Center in Houston, Texas, but for some time now has been actually supporting us here at the Kennedy Space Center, helping us get the Commercial Crew Program communication off the ground. Lots of pun intended. Kyle, thanks for joining me.
It's great to be here, Joshua, with you virtually.
Yeah, I know we're at this same center. Quick history. I know we started roughly a decade ago as the shuttle program was winding down. What's happened since then?
Yeah, well, that's exactly right. There, in the background, there was actually overlap between shuttle and the start of the Commercial Crew Program, this new way of doing business that NASA was transitioning to through what became the Commercial Crew Program in April of 2011. And then, of course, from that point forward, went through several stages of development where we kind of narrowed companies down until we got to the two that we've officially contracted with in 2014.
Kyle, you mentioned we downloaded to two specific companies back in 2014, 6 years ago, Boeing and SpaceX. Obviously, SpaceX is on the cusp of their operational flights, which we're super excited for. Boeing is very close behind, so excited to have them on board as well. What's the future of the program on a broad scope? When does it end, and how do we declare mission accomplished for this program?
I mean, obviously, you can define success in a lot of different ways. This program, I think just the sheer evolution of Commercial Crew and this new way of doing business has proven to be a great success. You know, as this partnership between NASA, SpaceX, and Boeing, we're going to be rotating expedition crews on the International Space Station on a regular basis, and that's the ultimate goal of the Commercial Crew Program, is to provide, you know, kind of that sustaining human path to and from the space station, so that we can continue all the research and science and internal and external that we're doing to eventually carry us on to deeper space missions.
As we think about low Earth orbit and NASA's role, why wouldn't we continue to fly astronauts to and from space station? Why not keep flying the space shuttle or fly another small rocket for that purpose?
There's different answers to that. One is, you know, as a government agency, and with this new concept of how we're managing the Commercial Crew Program, sharing costs, you know, we have a fiscal responsibility to taxpayers to try to, you know, essentially in this case, fly to and from low Earth orbit and to the International Space Station in as cheap a way as we possibly can. You know, somewhere learn through science and the activities on the space station as to how to live in low Earth orbit, so that we can learn how to live for a longer duration. NASA's able to kind of transition some of the other funding to what we really want to do on the NASA side, and that is to head to deep space, go back to the moon as a way station to eventually getting to Mars and other deep space missions, eventually, obviously, with humans.
All right, Kyle, as always, it is a pleasure to be working with you. Grateful for your support for us. Thanks for all you do for the program.
Absolutely. Thanks, Joshua. Enjoyed it.
A huge thanks to both of our guests, Kevin and Kyle, today. They are the tip of the iceberg of an incredible program with incredible history that's just becoming more and more storied every day. I'm excited for them and what's to come with Crew One and beyond. Again, the whole point of this series is we're talking about getting into deep space exploration. So please join us in a couple weeks. We'll be touching on the Mars 2020 mission and how Launch Services Program with the Robotic Explorers is helping us prepare to send humans to Mars. Until then, stay safe, be healthy, and don't forget that even the sky isn't the limit.
Flying cars, drones delivering pizzas, and a highway in the sky are scenes from science fiction. But they're also visions of our very real future.
Because we also move this in and then that in.
At NASA Langley Research Center, NASA engineers are laying the foundation for safe, autonomous flight in the national airspace through a project called Pathfinder. The goal of Pathfinder is to take separate urban traffic management projects and combine them into a single autonomous vehicle. Then have that vehicle fly and communicate with other autonomous vehicles in the airspace.
Going back a couple of years, we did a lot of on-vehicle testing. So we were testing things like Icarus, which is an autonomous sense and avoid, or maybe an autonomous flight management system for UASs, as well as Safe to Ditch, which is an autonomous safe landing or autonomous crash management system for UASs.
Combined, these systems will greatly decrease the risk of unmanned systems flying near manned aircraft, as well as safety risks for people below. To test this, researchers created incursions, where one drone flies too close to another, and then examining 3 different means of separation.
One is just manual, where the UTM operator has to get engaged and see that there's an incursion coming, and then issue a command to the ownership vehicle to maneuver out of the way. Another form of air traffic separation we looked at in Pathfinder was called geofencing. And the third level was autonomous sense and avoid. And that engages another area of Icarus.
Icarus, or Independent Configurable Architecture for Reliable Operations of Unmanned Systems, is a major piece to this autonomous flight.
You need to be able to make decisions to avoid other intruders in the airspace, stay clear from no-fly zones, or if you're inside a no-fly zone, the UAV should know how to get out of it, and to reroute itself around obstacles and no-fly areas. So some of these functionalities are essential to operate autonomously without human intervention. And so that's where Icarus comes in, and it provides those capabilities for UAVs.
As researchers conduct flight tests in the field, another piece of the Pathfinder puzzle is taking place in a separate location.
Copters beginning turn to the east.
Similar to an air traffic control tower on a standard runway, NASA Langley's Air Traffic Operations Lab is monitoring and making control decisions of active UAV flights.
These operators are observing their own vehicles, their own small drone, and they're also observing vehicles that are operating near their vehicle. So the goal is to make sure that they maintain separation from all other vehicles.
Originally, these volunteer operators were going to be monitoring from the field. But after a unique communications link was created to connect the ATOL with the vehicles on the range, participants can now monitor the vehicles and traffic from afar.
This was sort of a first step for us. Ideally, in the future, we'd like to expand on this capability because it has a lot of potential. We have a lot of capabilities here in the ATOL for human factors research, and out at the certain range, they have a lot of capabilities for live flights. And by creating this link, we're really opening up the door to a lot of future research.
As Project Pathfinder nears completion, the team has moved from flights on the range to cross-center flights, taking off from the roof of a central building and then autonomously flying out to the range.
It's exhilarating, really, to watch a system that you worked on. You've developed the algorithms, and then to see it perform out there. It's really a joyful experience.
It was a great team. Everybody was really putting in a lot of effort to bring this all together. So that was really something I'll remember going forward from this project.
Meters to copter turns north.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather.
Hi, everyone. My name is Brandon Rodriguez, and I work at NASA's Jet Propulsion Laboratory in Pasadena, California. I'm joined today by my colleague, Lyle Tavernier, who works in the education office with me. Today, we're here to talk to you guys a little bit about how NASA explores our Earth and our Earth's health from space. And the real push today is actually to hear from you guys. So this is our first session opened up the classrooms where we really want to hear the questions that you students have for us. How can we answer some of the questions you might have about Earth science and what it is that NASA is doing to explore this? Before we get into that, you guys probably know NASA as kind of looking out into space. You think of things like astronauts, or here at JPL, we talk a lot about going to Mars and exploring our solar system using cool robotic missions. But the truth is that outside of this work, really, we spend a good chunk of our time, a good amount of research looking at Earth from space. All sorts of crazy, cool new missions, whether they're actually here on the planet or orbiting our planet and kind of looking downward. And I think this is really important for young kids to understand, is that when you think about a career at NASA, it doesn't mean astronauts. It doesn't mean traveling outside of the solar system. Really, you can have a really exciting career being in space and looking down and better understanding this planet here. A lot of people might wonder, why is it that you kind of see all this focus on exploring other planets and living on Mars and all this when we have so much left here to understand as well. To that end, we actually have several talks coming up, including this afternoon. We'll be joined by the Ocean Exploration Trust, and we'll hear from the Nautilus Live as we talk about current research that's being done in exploring both our ocean and how we can extend that to oceans that we know about in space as well. But for today, we really just want to explore our planet. I think one of the really exciting things is to look at how our planet's health has changed over time. And this is obviously a big issue when you hear about things like global warming or climate change. And as a teacher myself, a physics teacher, one of my favorite missions looking at this is actually the GRACE mission. And this is a really, really cool mission that uses, kind of starts from this high school physics idea of following gravity. So what if we could orbit our planet and understand the mass of what's below us? Now, you might think, well, the mass doesn't change. And that's kind of true overall, right? Our Earth weighs the same, has the same mass. But where that mass is located changes. And where does that happen? It happens as ice melts. So as ice caps melt and that water kind of moves across to other places, the gravity in between these two, our orbiting GRACE and the ice cap underneath changes. That's really cool. Like, what a smart idea. And it kind of all stems from a basic high school equation that we teach in physics class, that the force of gravity is, the product of mass 1 and mass 2 divided by the distance squared, like a very simple equation. And that was enough to kind of get us thinking, like, wow, what cool ways can we track our planet from above? We do this with a slew of many missions. We have actually really dozens of missions exploring our Earth's health and kind of following climate change. Some of these include things like tracking Greenland ice and observing how that melts over time. As you guys know, with seasons, that ice level can kind of come and go. And this might give you the idea that, it goes down in the summer, but it comes back in the winter. And that's only partially true. Really what you want to be able to track is how that kind of variance, that up and down, changes over time. So is it melting the same amount every year? Is it recovering the same amount every year? And what we're finding is that's not true. So instead, we're melting more and recovering less in the colder months. So you can kind of track, again, how the local trend might be kind of up and down, but the overall trend over time is showing less and less ice in these regions. We follow this for Antarctica as well, following the Antarctic sea ice minimum. And one of, I think, is the most pressing things for us out here in LA, or if you live in a coastal area, is following sea level rise. And this is something that we have so much data on, and we actually have many lessons on our education website to track this and several of the other topics, where you can actually pull the data over the last several decades and take a look and see how has sea level changed over time. again, as you look at kind of small windows, you might say to yourself, oh, it's only going up a little bit, just a tiny bit every year. That's true. But over 100 years, over 200 years, this starts to really add up. And if you live near the water, all of a sudden you're going to see that impact. So I think it's a really exciting kind of area of expertise that we don't really talk about much when we think about working at NASA. And it's really, really important to say, studying Earth and our home, our one precious home, is really just as, if not more important than exploring out into space. So with that, I want to answer some of the student questions. If you guys registered for the Menti, the code was sent out to your teachers. And if you guys want to enter in questions, I'll make sure to address each of those for you guys. Looking at the some of these here, the first one is how is it that we can study Earth and outer space from outer space, and how we study our oceans? And that's a really, really tough question. So the cool news about that is that as an engineer, you might be able to craft all sorts of crazy new missions. Some of them, like the GRACE mission, I said, are kind of, I'm sure the people working on it would disagree, but it's conceptually kind of an easy thing, right? Where we're not talking about billions of dollars to kind of put this together. It's really just two boxes, right? Two boxes floating through space with a very, very precise laser in between them. And all of a sudden you're able to tell so much information, again, about the ground below. But they don't all look like this. Every Earth mission is really studying something very different, and therefore you have to study it in a very, very different way. So, for example, if you want to follow something like moisture in the soil, you use a very different type of instrument for that, like something like the SMAP mission, which looks at the kind of effectively the time it takes for a signal to hit damp soil versus dry soil and be able to bounce back to the orbiting satellite above. So every kind of mission has a very different way of looking at things. And again, I mentioned that you don't have to be in space to study Earth science. So you can actually be out in the field. You can be on the ocean. You can be on a boat. You can deploy buoys and look at things like ocean salinity. How salty is the ocean, right? That's one of the key characteristics you guys know about it is that the oceans have a certain amount of salt in them versus freshwater things like lakes and rivers. Ocean acidification is a really, really important one. I'm a chemist as my background, so I've always really been interested in that. Being able to track the pH, how much acid content is in these oceans. Now, again, for us, we might say it's not really that big of a deal, right? Like we're not swimming in an ocean that is so acidic that it hurts us. But if you're thinking about things like ocean life, that's a really big deal. Small changes for fish and coral can really make a big, big difference. And we want to be able to keep those things safe. So even tracking these tiny, tiny changes, like I said, give us an indicator for possible consequences later on. And there's no one way to do that. We do that through many, many different methods. I will say, to kind of finish answering this question, that actually the fact that we do so many different things is probably one of the best things. Because if you're a scientist and you do an experiment and you find, let's say you find a conclusion, it's really helpful when someone else does a very different experiment but gets to the same conclusion. Right? Imagine if you were talking with your friends and you all agree on the same thing. Well, that's good, but it's much more helpful if someone you don't know comes to the same conclusion, because you can say, oh, it's not just me, it's not just the people I talk to. Everyone in the field, all of these scientists agree, no matter what experiment you do, we all come together to the same answer. Well, then you know this must be a very strongly evidenced scientific conclusion. In science, we call this orthogonal. This means like our methods are completely different, but we all come together in the end on the same conclusion. It means it's a very, very strong conclusion. On the educational website, we have lessons exactly built around this. So you can look at greenhouse gas emissions and how those greenhouse gas gas emissions have changed over time. And following that over time, at the same time, we have the data for things like sea level rise or global temperature, the mean global temperature across the Earth. And again, if you start to see these correlations, you say to yourself, maybe these three things come together. Maybe there's a relationship between greenhouse gases and global temperature and ice melting and so forth. Really, really good question. And so many exciting careers, whether you're, again, an oceanographer, a chemist like me, or an engineer building some of these devices, just a multitude of careers at NASA looking at Earth science missions. Another question here is, how can we study earthquakes from space? And that's a really cool one too. Very, very tough question. I have very, very little knowledge in this space, so I don't know much about earthquakes. I do know that there is an extensive system here on Earth for earthquakes. And in fact, one of the ways that we learn about our Earth as a whole was from earthquakes. Maybe you guys know or have learned recently. I remember learning this in school, that one of the big questions was, what is the inside of our Earth made of, right? It's far too deep for us to just dig a hole, right, and take a look. So no one's been there. So how do we know what's inside? Or then maybe later, an even tougher question, as you guys get older, how do we know the thickness of the layers, right? I know a lot of us might think of things like crust and mantle and core, but how do you know how thick each of these are? And as any good Earth scientist will tell you, that crust, mantle, core is a little too simple. There's actually many more layers in between too. So how do we know? How do we know how thick? How do we know what's inside? And how do we know whether it's a liquid or a solid? And we use earthquakes to be able to study that. I think you guys will learn in time, if you haven't already, that there are different types of waves from earthquakes. There are P waves, primary waves, and S waves, or shear waves, secondary waves. And these tell us a lot about what's inside and how thick each of these layers are. So that's always a good way to kind of start. And because now we have these seismographic stations all over the Earth, we can track where earthquakes take place and how long it takes for them to reach different places across the Earth and following the speed of those waves. So studying earthquakes is a big one. It's a huge, huge area here on Earth. From space, you also you can learn a lot about what's inside the planet by, again, going back to the physics world, which tells you a little bit about the density and the gravity that each planet has. So when we think about how do we know that Earth has, for example, an iron core, we know that because iron is magnetic. So there are, thanks to, it's very, very important that there's a magnetic kind of center of our planet, because it allows us to have protection from solar radiation and helps us keep an atmosphere. So from space, we actually study planets, Earth and beyond, to see what's going on inside. How heavy is this planet? We know that the rocks on the surface of Earth are not very dense. They might feel heavy when you pick them up, but they're nothing compared to the density of of our inner core, our iron and nickel-rich core. So we are able to tell from space that the gravity of our planet is such that there must be something very, very dense and strong in the middle. That's how we figured out we had this dense core. Otherwise, looking at some missions here, the really cool thing about the number of missions we have is that, again, like I said, they study so many different things. So the mention of just how diverse these missions are give us a lot of opportunities to look at different things. And like I said, the scale of this is very, very slow, right? So I think one of the things that's tough for students and the general public to understand is a sense of urgency. When you think about how important this is, when you have all of these missions giving us different data, but it is this kind of tiny amount today or this year or even in 10 years, and they say, That's not very much. Oh, a couple millimeters a year of sea level rise. That's not that important. Again, sure, it's not that important today, but by the time it becomes important, it's too late. So we have to do something now. We have to act now in order to avoid consequences later. That's one of the really important things. So when we look at things like, I see a question here about how is it that you measure sea level from space? Again, we're able to do this through so many different ways, right? Again, here on Earth in space, where we're tracking kind of the flow of water, we're tracking ice melting. We use that GRACE mission to understand where water is, for example. All of these things, as this is mentioned in the question here, it's not like someone's out there with a ruler and saying like, oh, it's a little bit higher today, because the game isn't today. The game is trends. It's looking at what's happening over time, and because we live in a time where we're so busy and we're stressed and thinking about all these other things that are happening, we might not think about 10 years down the road or 50 years down the road. But it is really, really important. And being able to kind of have some foresight is really critical. So with that being said, I'll tell you guys, as students, any little change you can make might really have an impact too. You think about, again, a little change that's bad news, like sea level rise, is going to be compounded in decades from now. But also a little change you make today that's helpful will also be compounded. So doing little things can actually be really helpful down the road too. So, take a look around and think about how you can help. Whether it's just like remembering to turn the lights off, or not taking a long shower, or reusing your water bottles, right? Not creating a bunch of plastic waste and things like this. There are just so many little things we can do to help. And if we all do a little bit, they're going to add up quite a bit too. I'll take a look at another question here. So another question I see here is looking at, again, how you guys are going to be part of NASA later on, whether you're here or if you're an international student. And there are so many positions for you guys. We have so many avenues for you guys to come be part of this. In fact, just last month, we had a talk from a speaker who was an international student before coming to JPL. And, he told a really nice story about how his path to JPL kind of goes through, it all goes through school. That's like the great kind of door opening way that you can get any job you want in science, really, is you just kind of go to school, you find these opportunities, and you kind of strike whenever an opportunity presents itself. So some of you guys might be very young and saying, this is so far away, but kind of the theme of the day, you start small now, and then you get to see big rewards later.
My land cover career really started in 2002 with biggest wildfire in Oregon's history, and that was the Biscuit wildfire. I, at the time, was doing botany surveys and looking for rare plants or rare mushrooms, and so I was spending a lot of time out on the forest looking at and taking photos and doing the documentation that a scientist or a land manager does. When that fire happened, it changed everything. We all had to react to this fire that was burning up